Hey everyone, and welcome to This Explainer. Today, we are embarking on a really fascinating journey into the absolute foundation of modern digital trust. We're going to pull back the curtain on the underlying mechanics, the hidden security flaws, and the incredible evolution of distributed networks. So if you've ever found yourself wondering how systems like Bitcoin actually get total strangers to agree on reality, well, you're in the exact right place. Let's dive right in.
Think about this for a second. How do you establish trust when literally anyone in the room could be lying to you? Now, this isn't just some abstract philosophical riddle. It is the fundamental, seemingly impossible challenge of distributed computing. When you've got a network of computers spread out all across the globe, some of them are going to fail, some will just randomly drop offline, and some might be actively trying to deceive the rest of the network.
Computer scientists actually formulated this challenge way back in the 1980s, and you might already know it as the Byzantine generals problem. The idea is, imagine a group of generals surrounding a city and they absolutely have to agree to either attack or retreat together. But here's the catch. Some of those generals are traitors, and they're intentionally sending out false messages. So how does the loyal majority reach a consensus? This classic dilemma, which was first introduced by Leslie Lamport, forms the absolute baseline foundation of every modern consensus algorithm out there. You simply cannot build a distributed network without solving this first.
So here is our roadmap for today. 1. The distributed consensus problem. 2. PBFT, which was the first practical solution. 3. Proof of work's heavy cost. 4. Proof of stakes vulnerabilities. And finally, number 5, the future, covering tangles and trade-offs.
Starting with Part 1, the distributed consensus problem.
At its very core, a standard, linear blockchain is basically trying to get a group of completely independent participants to agree on which block comes next, linking them all securely using cryptographic hashes. But the whole system is locked in this constant tug-of-war between two main properties, safety and liveness. Safety makes sure everyone agrees on the exact same data without any conflicts. Liveness, on the other hand, ensures the system doesn't just freeze up, meaning it actually keeps adding new blocks. And balancing these two things in an asynchronous network like the internet, it's incredibly difficult.
Moving on to Part 2, PBFT, the first practical solution.
So let's flash back to 1999. Researchers Miguel Castro and Barbara Liskov finally figured out how to make Byzantine fault tolerance efficient enough to actually use in real-world services. They created PBFT. Instead of a totally chaotic cascade of messages flying between nodes, PBFT relies on a primary leader and a set of secondary backups. It swaps out heavy digital signatures for lightweight message authentication codes, or MACs, and it runs on a super efficient three-step pipeline: pre-prepare, prepare, and commit. The brilliant part is, even if that primary leader turns out to be malicious, the honest backups will only move forward when they see enough agreement. It basically took all that chaos and collapsed it into a highly organized, highly efficient system.
But, PBFT definitely has a catch. It's a deterministic consensus, which means it highly favors safety over liveness. If the network gets disrupted, PBFT will just halt completely rather than risk an inconsistent state. Now, Satoshi Nakamoto made a massive philosophical pivot when creating Bitcoin. He designed a probabilistic consensus, what we know as proof of work, which flips that entirely, favoring liveness over safety. It ensures those blocks just keep on coming, even if it risks temporarily creating conflicting paths or forks, which just get resolved later on.
Which brings us to Section 3, Proof of Work's heavy cost. The absolute crucial point to understand here is that proof of work secures the network by making it physically expensive to participate. Miners are literally forced to solve these computationally costly mathematical challenges. By requiring all that brute force computing power, the protocol naturally deters malicious actors. Why? Because attacking the network would simply cost way too much money in hardware and electricity to even be worth it.
7. Just 7. That is the incredibly, almost shockingly low average number of transactions per second that the Bitcoin network can actually handle. When you compare that to centralized credit card networks, which easily process somewhere around 2,000 transactions per second, you instantly see the massive performance bottleneck that proof of work introduces.
And unfortunately, that performance bottleneck isn't even the biggest issue. The annual energy consumption of the Bitcoin proof of work network actually rivals the power usage of the entire country of Switzerland. Since miners are essentially locked in an arms race of brute force computation, a monumental amount of environmental and physical resources is required just to maintain trust in the system. And the crazy part, most of this energy is basically wasted on mathematical guesses where only one winner actually gets the reward.
That leads us into Section 4,
Proof of Stake's vulnerabilities. Enter Proof of Stake. This system attempts to fix things by substituting physical energy with virtual capital. So hardware miners are replaced by token validators, and your probability of proposing the next block is tied directly to the assets you're willing to stake. This drastically reduces the energy consumption and shoots throughput up to hundreds of transactions per second. But, and it's a big but, by removing the physical cost of failure, it introduces a whole new set of really unintuitive security loopholes.
Probably the most famous loophole is known as the nothing at stake problem. See, in proof of work, dividing your computing power between two different forks cuts your chances of winning right in half. But in proof of stake, validating a block costs absolutely zero physical energy. So if the chain happens to fork into path A and path B, a purely rational validator is just going to bet on both outcomes. By voting on all the conflicting paths, they maximize their chance of getting a reward without spending a single dime. And as you can imagine, this makes reaching a final consensus incredibly difficult.
And this costless voting loophole directly enables something even more sinister: the long-range attack. Because generating blocks doesn't cost any electricity, a malicious actor who happened to hold a lot of tokens in the past can literally go back in time, create a fork at an old block, and instantly generate an entirely new history that's longer than the real one. They can effectively rewrite history without paying the massive electrical penalty that proof of work would demand for doing the exact same thing.
Let's look ahead to Section 5, the future, covering tangles and trade-offs.
So how are developers trying to solve this? Well, one approach is delegated proof of stake, or DPoS, which is used by systems like EOS.io. To achieve massive speeds, we're talking up to 4,000 transactions per second, DPoS actually reintroduces a degree of centralization. The community basically votes to elect a tiny handful of delegates, often just 21 individuals, to run the whole network. While it is undeniably fast, the glaring trade-off is the severe risk of collusion among a few wealthy stakeholders, plus a really high vulnerability to targeted denial of service attacks against those specific known delegates.
Now, another approach abandons the linear blockchain entirely. This is the IOTA tangle. It uses something called a directed acyclic graph, or DAG. It looks kind of like a massive spiderweb because it eliminates miners completely. To issue a new transaction on this network, you are actually required to validate two previous transactions yourself. This clever design allows participants to publish transactions concurrently and asynchronously, creating this massive interconnected web of validations.
The tangle represents a totally alien architecture. By forcing users to work for their own transactions, it achieves theoretically unlimited scalability and allows for completely free micropayments, which is absolutely perfect for the Internet of Things. But again, there's always a trade-off, right? It relies heavily on constant, massive user engagement to stay secure, and it introduces some pretty complex vulnerabilities, like offline parasite chains that can theoretically trick the network.
So let's bring it all together. Whether we're talking about the massive energy drain of proof of work, the complex loopholes of proof of stake, the limited scalability of PBFT, or even the highly experimental risks of the tangle, the reality is there is no perfect system. When it comes to distributed consensus, you're basically looking at a menu of trade-offs between speed, security, and true decentralization.
Which brings us to our final question today. When we look at actually building out the digital infrastructure of the future, the choices we make right now are going to define how our internet operates for decades. So I'll leave you with this to think about. What matters most to you? Is it absolute, unyielding security? Is it maximum, frictionless speed? Or is it true, borderless decentralization? Think about which trade-off you are most willing to make. Thank you so much for joining me on this explainer, and definitely keep questioning how our digital world is being built.